The Faculty of Engineering, LTH, at Lund University is home to over 1,000 researchers and PhD students working in classical engineering subjects as well as in newer fields, making links with areas such as medicine, science, finance, environmental science and design. Examples of new technologies that have been developed at LTH include the medical ultrasound, the inkjet printer, Bluetooth wireless communication and health-promoting foods such as Proviva and Oatly. And now let's visit the amazing virtual reality lab.
The virtual reality lab is located in the Department of Design Sciences. We deal with lots of different visualization projects. They can involve anything from visualizing historical settings to future buildings and outdoor environments. We will show you a clip about Pompeii based on 3D scanning. This was done in collaboration with the Department of Archaeology and the Humanities Lab.
Take a deep breath and think about what you now have in your lungs. Sure, it's air, of course, oxygen, nitrogen and such, but there is also something else. In each cubic centimeter of air you inhaled, there were thousands of particles, all of them too small for the naked eye. These are what we study here in the aerosol lab at the Division of Design Sciences. Particles are literally everywhere, especially in urban areas, but the air is not particle-free anywhere on Earth, nor has it ever been. On average, you do inhale some 100 billion particles every day. Many of them are exhaled again, but the smallest particles can follow the airstream all the way down to the most vulnerable part of the lung and stay there. And we do know from epidemiology that airborne particles cause several diseases, not only in the respiratory tract. But what these studies cannot tell us is if it was the particle size, the shape, the chemical composition, or some other particle property that caused this harm. We try to figure out what it is that makes some particles dangerous and some not. We work together with medical scientists and together we conduct human exposure studies. We place volunteers in a very well-controlled chamber and let them breathe in air with normal levels of common particle types. A type of particle which we know every possible characteristic of. We then look for effects in these humans, which could tell us that there was something about that particular particle type that made the body react. By trying several kinds of particles in this way, we hope to figure out what it is that makes some particles dangerous.
How do you make a computer look like you and me? No. Not look like you and me, to see the way we do.
Computer vision research is aimed at developing computer programs that can extract information from images and video. This is a multidisciplinary field in many ways. Partly this is because we need competences from many different research areas in order to solve our problems. But partly this is because computer vision can be used to solve problems in many different areas of research and society. One theme within computer vision is the desire to understand the human visual system and to be able to duplicate those functions. This could, for example, be algorithms that can find the different objects within a scene and to understand in which context the image has been taken. For some of these tasks, the computer vision state of the art is much inferior to the human visual system. But there are areas where computer vision research is really good. For example, for searching within millions or billions of images for a particular CD cover or book cover. Another example where it's really good is for extracting 3D information from images. My main research area concerns the 3D modeling from images. Here's an example of images from Örebro Castle in Sweden. We see 4 images, and in each image we've detected so-called interest points, and the interest points are marked as red dots. Then we have other algorithms that can find the matching of these red dots between consecutive images. These matchings are here marked by green. Once we have the interest points and the matches, then we can use other algorithms to calculate both the position and the orientation of the camera for each of the images and the 3D structure of the interest points. This is what the result looks like for a couple of hundred images of Örebro Castle. You can see the 3D structure of the scene, and you can see the position of the camera for the individual images. Once you have such a 3D model, you can refine the model by adding texture to get something that looks like this. Another theme of computer vision research is trying to automate processes in medicine and industry. This could, for example, be helping doctors interpret medical image using medical image analysis. It could be helping robotic researchers by developing vision for robots. And it could be helping traffic researchers understand behavior of traffic by analyzing video. We work with several different areas of society to ensure that the research gets to use. And this is where I think it's the most fun and most stimulating. Every day we get to meet experts from different areas and we get to discuss how we can help them solve their problems using computer vision research. And this is really fun.
Atom physics open your eyes to a world that has been known to us for a long time, but that we have not yet been able to see, the world of electrons.
At the High Power Laser Facility, Atomic Physics, Faculty of Engineering, we are creating extremely short light pulses through the interaction between atoms and intense laser light. We measure the duration of these pulses in attoseconds. 1 attosecond is 10 to minus 18 seconds. 1 attosecond is to a second what a second is to the age of the universe. These pulses are created through the generation of very high order harmonics of the laser light. We use attosecond pulses to study dynamics in matter. You can view these pulses as short flashes, allowing us to take a photo of something moving very fast. If the flash is too long, the photograph will be blurred. If, on the other hand, the flash is short enough, you will be able to take a sharp image. By using light pulses as a pump to initiate a fast process, and sometime later as a probe to analyze it, and by varying the delay between pump and probe pulses, one is able to capture a motion in a very similar way as with a stroboscope. The motion that we want to look at is that of electrons in atoms, molecules, or on surfaces. We have a relatively large research group with about 20 persons, including 10 PhD students and 5 postdocs, coming from all over the world, especially from Europe. We have 3 different laser systems to generate attosecond pulses. One of them is the most powerful in Scandinavia. Our goal is very fundamental. We are driven by curiosity. What we study leads to better understanding of the interaction between light and matter, which is very fundamental in our world. We are also doing technical research where the techniques and instruments that we develop might be useful in other, more applied areas.
What does a car engine look like from the inside? Well, most of us have never been inside one. But here at Sweden's biggest research lab for combustion engines, this is all in a day's work. Is this really a microphone?
Combustion engines are everywhere in modern society. You find them in cars, trucks, ships, airplanes, and power plants. But combustion engines are so complicated that still, after 150 years, there's a lot to be learned in order to make them as fuel efficient and environmentally friendly as possible. New possibilities for intelligent control of the engines are also constantly emerging, thanks to the rapid development of electronics and computers. The research at the Department of Energy Sciences, Division of Combustion Engines, aims to understand and control the combustion in engines. Detailed information about the combustion can be gained by making part of the engine out of glass. Advanced laser and imaging technology is used to study reactions and flow inside the combustion chamber. Leading-edge research in this field takes place here in Lund. An optical engine, where part of the combustion chamber is made of glass, is used to study the details of the combustion. In this setup, the top of the cylinder is a glass ring, and down here we have a mirror that makes it possible to photograph up through the glass piston top. By doing so, we can see, for example, where the fuel is during the combustion. It's also important to understand the interplay between fuel and combustion, such that, for example, biofuels can be used in the best way. Optimal combustion requires very accurate control of the fuel injection. For this reason, we measure and analyze, for example, the pressure inside the cylinder and use the information to control the fuel injection in the best way. The proof of success is provided by measuring fuel consumption and exhaust composition with advanced measurement equipment. Combustion engine research in Lund is mainly conducted by our PhD students, and they are part of a research group consisting of approximately 30 people who study combustion in engines. The largest part of the research group belongs to the Combustion Engine Division, but we have very active collaboration with the Division of Combustion Physics and the Department of Automatic Control, as well as with the divisions of Fluid Mechanics and Heat Transfer within our own department.
What vehicles will we use for transportation in the future? Well, this is one of the important questions at the Transport and Roads Division.
This is a hugely exciting area that affects us all in society. What the transport system of the future will look like. We already know that our travel patterns of today are not sustainable in the long term, and that much has to be done to reach our climate targets and to make our towns and cities more attractive and less congested places. I work at the Transport and Roads Division of the Faculty of Engineering. I teach and research on how we use today's transport system, but perhaps more especially what the future transport system could look like. My research focuses a lot on how the planning of transport systems in cities could be changed so as to encourage more people to walk and cycle and take public transport. Our research has shown, for example, that the route is highly important for cycling. It doesn't help if we have good cycle paths which only run for part of the way. They have to run all the way from A to B. This is important in order to make cycling attractive. But as another example of how planning must change, we can also look at out-of-town shopping centres. Today, these are planned for the car, with good access for the car as a norm. But a cyclist must often instead travel in a roundabout way to find bike parking, which is usually situated at the back of the shopping centre. Perhaps it's even worse for a public transport passenger, who has to get off at a stop far away from the shops and then find their way through the parked cars to get to the entrance. And this just shows how we must increase the quality and the attractiveness of other modes aside from the car, so that we can also choose these when going to, for example, an out-of-town shopping centre. This could also be seen as a question of fairness, as even those without a car should be able to get to shops and other activities by another mode which is just as convenient. Even more important is the proportion of young people today who are choosing not to get a driving licence. This proportion is increasing fast, and if we don't wish to force them into a car-dominated society in future, we have to give them good pedestrian and cycling access in addition to access for the car. Our lab is today's transport system. We go out and we look at how people use transport today, we study behaviour, we measure speeds, we do interviews. All of this is done to find out how people use the transport system today, and in particular, what is needed for us to change our travel behaviour in the future.
How can you find one single cancer cell among 1 billion healthy blood cells? Well, I don't have a clue. But there's someone who thinks he knows.
I'm involved in very exciting research at the Faculty of Engineering, where we develop new microtechnology within the medical technology areas ICET and acoustophoresis. The research field is called Lab-on-a-Chip technology, which means that we study what benefits you can make by reducing the analysis volumes down to microliter or even nanoliter volumes. This can be compared to taking a droplet of blood that is about 100 microliters and split it into more than 100 fractions for analysis if we're really good. Our Lab-on-a-Chip research is focused on speeding up the way we analyze blood samples. By analyzing many parallel samples, there are evident benefits to be gained in disease diagnostics. By combining nanovials on a chip that captures different biomarkers, we are able to tailor-make a chip to identify a specific disease such that we can read a pattern from the diagnostic chip that gives a more clear picture whether a patient has a disease or not, and maybe even predict the state of disease progression of the patient. An equally exciting development in our research group is our work on sorting cells in microchannels on a chip by the means of ultrasonic fields. The technology is called acoustophoresis and is based on the fact that specific cell types move at different speeds in an ultrasonic field, which is dependent on the individual acoustophysical properties of each cell type. With the help of micro and nanotechnology, we can now make microchannels that are only a fraction of a hair in cross-section. A thrilling application of this research is the possibility to trace cancer cells in the blood of cancer patients for diagnostic purposes. The measurement of cancer cells in blood has recently become a standard diagnostic method, and it is used both to get an indication of the disease stage and also to monitor if the prescribed treatment is efficient. The major challenge is to be able to detect the cancer cells in the blood, who may only be present in numbers less than 10 cells per 1 billion blood cells. It is an enormous challenge to find the right cells in this jungle of healthy blood cells.
No. At the NanoLab, research is conducted on objects that are 1 billionth of a meter in size. That's small.
Nanoscience is about discovering and using the new phenomena that occur in extremely small structures of a material. Scientists at the Nanometer Structure Consortium at Lund University and its Faculty of Engineering are world experts in creating such very small structures with extremely high control, almost atom by atom. For example, these nanowires are needles that are about 1,000 times thinner than a human hair. They are produced in this very clean environment, protected from less clean humans, and can be used in a broad range of applications, including solar cells that require much less material than traditional solar cells, or as light sources that use much less energy than light bulbs. In my own research, I make use of the random motion that every small object carries out when it gets kicked by air or water molecules. This is called thermal motion. For example, we are learning how to convert heat into electricity by using nanowires to direct the random thermal motion of warm electrons into one direction, generating a current. With this effect, called thermoelectricity, one hopes to be able to generate electricity from waste heat, for example from the heat from car engines. Molecular motors also make use of thermal motion. They are large molecules that perform useful tasks in living cells, for example the transporting of other molecules. We are learning how to build such motors from scratch. And working together with our colleagues at Kalmar, we learn how to control the motion of biological motors outside of cells. For example, we can use molecular motors to transport individual molecules through hollow, nano-sized tubes. Such systems may in the future be used to understand how human muscle works, or as part of miniature chemical laboratories, so-called labs on a chip, for quick and simple diagnostic devices in doctors' offices.
In order to fabricate these structures, we make use of state-of-the-art techniques such as electron beam lithography. With these tools, we can fabricate structures down to tens of nanometer precision. We can also control the growth of nanowires using a variety of material. In my work, I specifically focus on that material which is biocompatible. With this freedom, we can create structures such as biosensors for use in drug screening and for diagnostics.
The Robot Lab develops the workers of tomorrow.
Hello, Lata. How are you today?
Hello. Can you speak?
It's amazing. And stand up.
And it will fit both robots, so that's perfect.
Okay, fine.
Great. Robotics is a multidisciplinary topic, and therefore it's both natural and necessary for us at the Department of Automatic Control to have a close collaboration with researchers from other departments from the Faculty of Engineering. We also collaborate with colleagues from the Faculty of Medicine. Traditional robots, as we know them from the manufacturing industry, has successfully run applications like welding and material handling for decades. And automatic control in this context is much about finding algorithms for making the robot move faster and more accurately. However, we also study new concepts like this two-armed robot used for assembly operations. The robot is designed to be safe for human co-workers to share workspace with. And it also has facilities like contact control. So the operator can grab the gripper of the robot and move it and thereby easily instruct it in a new intuitive way. The contact force control also provides other benefits. So you don't have to exactly specify where workpieces are located in the environment, but the robot can search for it itself, and thereby being much more robust to misalignments and deviations.
Take the switch and put it on the table.
It can be expensive for companies to hire a robot expert every time they want to change something in their automated production line. Therefore, our group at the Computer Science Department at Lund University tries to make it easier for humans and robots to interact. In this experiment, we use natural language, that is, English, to instruct a robot.
We also work with teleoperation of robots. For instance, keeping the operator away from an unhealthy or dangerous environment. Another application of remotely controlled robots we find in medical applications like surgery. So already today, robots are used for medical surgery, where the surgeon controls one or more robot arms holding a scalpel, needle for sewing, or a scissor. However, it's the difference of controlling the scalpel by just looking where it is or by actually feeling it as if you were holding it yourself. And here our research on force control and haptic interfaces come into play. So we try to give the surgeon the haptic feeling back and also study how, for instance, network delays influence the performance. This is a so-called parallel kinematic robot. So unlike many industrial robots, which have the structure of a human arm, this has several rods meeting at the end plate here. So the construction is very stiff and rigid, and it can cover a large workspace, and the low mass of the moving part makes it very, very fast.
Metals are materials that have always dazzled us. And if you didn't know, there are both good and bad metals. And the bad metals, they're really good.
Metals. These are materials that we would normally consider to be simple.
Simple materials with simple properties. They conduct electricity, they are shiny and bright, and they are malleable. They also tend to be structurally simple. The materials that I and my research group are working with are quite the opposite. They're complex, they're hard, they're brittle, and their transport properties are really, really bad. And this makes them very useful as thermoelectric materials. Thermoelectric materials are materials that directly convert an electrical current into a thermal gradient, or vice versa. Uses a thermal gradient to create electrical power. The cooling side of thermoelectrics is quite widely used today, and we see it in the cooling of laptops, in mobile refrigerators for cars and automobiles, and in cooling plates in restaurants for milk or juice. What would be even more interesting is to use the other effect, that of converting a thermal gradient into an electrical current. It is being used today, but only in very special niche applications. Perhaps the most spectacular is in deep space probes. These are spacecraft that travel so far that the light of the sun becomes too weak to serve as a source for energy. Thermoelectric power generators are very robust, and they do not need any service. This is, of course, a fantastic advantage if you're going outside the orbit of Jupiter, where service personnel is very, very difficult to come by. And then when I short-circuited the flow across the CCD, what we strive for is better efficiency in thermoelectrics, because then we may be able to go from outer space to our highways, to be able to use thermoelectric power generation in our cars, to use the waste heat in the exhaust system to feed the generator of the car's electric system is the ultimate goal for thermoelectric research. The poor thermal conduction of the thermoelectrics is the result of a disturbed or complex crystal structure. And in order to fully understand how a thermoelectric material works, we need to understand what it looks like at the atomic level. But with the new facilities that are growing in Lund today, MAX 4 and ESS would give us an entirely new picture of what's going on, a deeper understanding, and a much better possibility to create new, better, cheaper, and more environmentally friendly thermoelectric materials. That is important for the future of us, for the future of the energy system, and for the future of the environment.
Cancer research at the Department of Immunotechnology is a great example of how technology and hospital clinics work towards the same goal.
I have performed research at Lund University since I graduated here 14 years ago. And to be a research group leader provides me with a tremendous freedom to explore my ideas, which is highly inspiring, but also demanding. Our research focus on cancer in the lymphoid system, and my personal driving force is the potential to gather novel information that can improve the possibilities to cure patients. This is achieved through the use of rapid technology development within the biomedical field and through collaboration with clinicians at the hospital. Such translational collaborations between university and clinic is the core of Create Health, which my research team is associated with. We are working with mantle cell lymphoma, an aggressive type of cancer that despite improved treatment methods have a very poor prognosis. Many patients respond to therapy, but relapse within short. Such recurrent tumors are caused by a small number of resistant cells that expand after or even during treatment. We have during the latest years shown that a certain protein called SOX11 is an important biomarker as it can distinguish cancerous from healthy B cells. And to be able to detect this protein in tissue, we have developed antibodies. These antibodies are now commercially available and enable physicians and researchers all around the world to use these novel tools. During recent years, treatment of mantle cell lymphoma has dramatically changed and prognosis has improved. However, alternative treatments are still needed for subgroup of patients, And we believe that our research can contribute with novel ways to find those patients, and hopefully in the future being able to offer curative treatment. Medical research requires diverse qualifications, and our move to Medicon Village in Lund is of strategic importance. Here we can work closely with other researchers focusing on the quest of curing cancer, but also together with startup companies that are located here.
Many researchers at the Faculty of Engineering are involved in the development of new bio-based products for different areas.
New and innovative biochemical processes will be used in future biorefineries to produce a large variety of products based on renewable resources. The products can be chemicals, fuels, or energy in the form of heat or electricity. This is an exciting area in which many researchers at the Faculty of Engineering are engaged. These researchers collaborate within the research platform LU Biofuels, which holds a lot of competence on biochemical process routes. The raw material is processed to the final desired product by first using enzymes to produce sugars from the biomass. These sugars are then microbially converted into other chemical building blocks. One such example is succinic acid, which can be used to produce bioplastics. The biomass used, for example straw, shown here, contains long cellulose chains. The biomass must first be partly degraded by heating it up to a few hundred degrees for a short time to enable enzymes to cut these chains into simple sugar molecules. The research involves collaboration with other researchers from applied microbiology, biotechnology, and biochemistry who develop new microbes and enzymes. Added capacity for new reactions, the ability to use more sugar varieties, or an improved tolerance of the microbes are examples of important improvements.
It is not obvious that all new bio-based production systems are environmentally preferable. To assess the total environmental performance, a broad system perspective is needed, including the complete production chain, from the production of the biomass feedstock, conversion, and final use of the product. This kind of evaluation is done by a so-called life cycle assessment, where the product is followed from cradle to grave. Examples of long-term sustainable biomass feedstocks are residues from agriculture and forestry, such as straw and logging residues, but also residues from food and forest industry. An efficient conversion of the biomass feedstock into high-value biofuels and chemicals makes it possible to maximize the environmental benefits at the same time as the feedstock will last longer. This will also normally lead to increased profitability. We in Sweden have, from an international perspective, very good conditions to develop these kind of new resource-efficient biorefineries.
Hello. What kind of houses will we build in the future? And after we built them, how will we heat them?
We all have a special relation to buildings. We live, work and study in buildings that have to provide a good indoor climate, regardless of the weather. At the same time, buildings are required to use a limited amount of energy to reduce the impact on global climate. The energy we use should also be environmentally friendly, renewable. To reach the climate goals, there are a lot of things we need to do and can do, especially since buildings account for about 40% of our total energy use. I work at the Division of Energy and Building Design with research and education on energy-efficient buildings. The research includes developing and evaluating concepts and technologies for energy-efficient buildings. Already in the 90s, I carried out analysis to find out if and how passive houses, thus buildings with a very low energy demand, could be implemented in a Swedish climate. This resulted in the first passive houses in Sweden, and after measurements and positive evaluations, the development continued with new applications and demonstration projects. Now, according to the European Union, We should reach nearly zero energy buildings for all new buildings from the year 2020. But how are zero energy buildings defined and how should they be designed? This is part of our research.
I'm part of our research team and I'm focusing on how architects and urban planners can implement solar energy in the design process. I've interviewed Scandinavian architects and have performed an analysis of the obstacles and opportunities of solar energy in the Scandinavian context. Now I'm focusing more on urban planners to support them with guidelines for solar energy planning. For example, we simulated the active solar energy potential of planned building blocks in Lund and Malmö.
We need technologies that are easy to use and with buildings that are attractive. Our research involves collaboration with the building industry and municipalities. Our knowledge is also disseminated within our international master program in energy efficient and environmental building design.
Hello. 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 Oh, well, everyone knows how sensitive wireless products are. But thanks to the development of electronics, constant progress is being made. Hello? Ah, there you are.
At the Department of Electrical and Information Technology, we have several really exciting research areas. One of those is electronics, my area, or more specifically, the design of integrated circuits, or what we daily refer to as microchips. When I designed my first integrated circuit during the second half of the 80s as a student, the transistor dimensions we used were 3 micrometers. Today, when we fabricate circuits, they are 28 nanometers. That is that the transistor dimensions has been reduced by a factor 100, with a corresponding decrease in power consumption and increase in speed. The integrated circuits are designed in the computer. After that, they are sent away for fabrications, which takes a couple of months. And after they return, we measure them in our research lab. The development of integrated circuits can also be exemplified by the development of mobile phones. When I designed my first integrated circuits, Ericsson launched their Harry Hotline campaign. In those days, mobile phones were purely analog. All we could do was talk, and there was no data transmission at all. What has made those accomplishments possible is the development of electronics and in-system design. Today we have electronics everywhere around us and even inside us. This can be exemplified by, for instance, the pacemaker, which was a Swedish invention, or we also have capsule endoscopy, where we swallow a pill that goes through our body and takes images which are transmitted wirelessly to the outside. At the department, we have or are trying to create new research projects within those two areas. The bulk of the research at the department mainly deals with some form of communication, mainly wireless communication. In this area, I'm also heading a research center or an industrial research center where we, together with our partners, try to develop the technologies of tomorrow. At the department, we have research areas spanning from the antenna. How do we design smart and good antennas? How do we understand the radio channel? How do we develop algorithms to transmit data over those radio channels? An exciting research project that is about to finish is called Wireless Communication for Ultra-Portable Devices, where we look at medical applications like pacemakers and hearing aids. Within this project, 6 PhD students from different areas has worked together to develop a completely new solution, with extremely low power consumption, which will increase battery life of such devices.
Here at the Department of Fire Safety Engineering, research is carried out on how fires develop and how they spread.
Research areas at the department within fire safety engineering are focusing on human behavior, support for fire services, extinguishing systems, risk analysis, and fire development, which is my research area. With fire development, we mean how a fire spreads after ignition of the first item. Fire spread is important because it determines, for example, how much time one has to evacuate the room, or how fast the room will be on flashover. That means when the complete room will be burned. How fast this will happen will determine the consequences of a fire on people and on property. Every year, almost 100 people die in Swedish residential fires. That means in their own home. The fire causes are often candlelights, cigarettes, cooking plates, electrical apparatuses, and chimneys. The cost for fires in Sweden is approximately 6 billion crowns per year. An important factor for fire spread is how quick a fire will spread in a building and how building products influence this behavior. As building products, we mainly think about wall and flooring materials, cables, and furniture. The first property one wants to know is how quickly the material will ignite if it is exposed to heat. After that, we want to know how quickly the fire will spread on the surface. That is the so-called flame spread. The flame spread depends on how the material is mounted, for example, vertically or horizontally. These two factors determine one of the most important parameters, and that is the heat release rate produced by material. Another important factor is the generated smoke, its content and its opacity. The content is important because the smoke can be toxic. The opacity is important because it determines whether we can see evacuation signs. Finally, we want to know if a material produces burning droplets when it burns. All these parameters will influence the overall fire spread and development, which is then used in advanced computer models to design fire-safe buildings.
We want to be a faculty of engineering where everyone is welcome. And we want to be a cross-boundary faculty, and we want to be a world-class faculty with great breadth. And we usually say diversity is our strength. What if we could clone ourselves? Then we would be even broader in research as well as in education.
As you just saw, here at the Faculty of Engineering, there are endless possibilities. And yet, this was just a small fraction of the compelling research conducted here.